Welcome to Aircraft Systems, based on Chapter 7 of the FAA Pilot's Handbook of Aeronautical Knowledge. In this module, we'll take a comprehensive look at the primary systems found on most aircraft. Understanding these systems is not just an academic exercise. It's a fundamental part of being a safe and competent pilot. You need to know how these systems work, how they interact with one another, and how to recognize when something isn't functioning correctly. Throughout this course, we'll cover the engine, propeller, induction, ignition, fuel, lubrication, and cooling systems, as well as the electrical system, landing gear, and environmental control systems. Whether you're working toward your private certificate or building on existing knowledge, a solid understanding of aircraft systems will make you a more confident and capable aviator. Let's get started. This chapter focuses on the core aircraft systems that every pilot must thoroughly understand to operate safely and effectively. We'll work through four main areas of study. First, we'll examine power plant and propeller systems, covering both reciprocating and turbine engine types, along with propeller design principles. From there, we'll move into induction and ignition systems, including carburetors, fuel injection, magnetos, and FADEC technology. We'll then look at fuel, oil, and cooling systems, which are essential to engine health and reliability. Finally, we'll cover the broader category of airframe systems, including electrical and hydraulic systems, landing gear, pressurization, oxygen, and anti-icing. Together, these topics form the foundation of aircraft systems knowledge required for competent and confident flight operations. As we move through each section, focus not just on how these systems work, but on why that knowledge matters to your decision-making as a pilot. An aircraft engine, also referred to as a power plant, serves two essential purposes. It produces the thrust needed to propel the aircraft through the air, and it drives the various systems that keep the aircraft operating safely and efficiently. There are four main types of power plants you need to be familiar with. First, the reciprocating engine works in combination with a propeller to generate thrust. This is the type most commonly found on smaller general aviation aircraft. Second, the turboprop also drives a propeller, but it uses a turbine engine to do so, making it well-suited for regional and utility aircraft. Third, the turbojet produces thrust by dramatically increasing the velocity of air as it passes through the engine. And fourth, the turbofan builds on the turbojet concept by routing a portion of air around the core of the engine, known as bypass air. This improves both thrust and fuel efficiency, which is why turbofan engines are the standard choice on most modern commercial aircraft. As we move through this course, you will develop a deeper understanding of how each of these power plant types functions and where each one is applied in aviation. Reciprocating engines are the most common power plant found in general aviation aircraft, and understanding how they work is fundamental to operating them safely and efficiently. These engines convert chemical energy stored in fuel into mechanical energy through a combustion process that takes place inside the engine cylinders. As fuel and air ignite, the expanding gases push the pistons in a back-and-forth motion, and it is that reciprocating movement that gives this engine type its name. That mechanical energy is ultimately transferred through the crankshaft to drive the propeller and move the aircraft through the air. Over the past 2 decades, computerized engine management systems have significantly advanced what these engines are capable of. Modern systems now optimize fuel delivery, monitor performance parameters in real time, and automate functions that once required constant pilot attention. The result is improved fuel efficiency, reduced emissions, and a meaningfully lower pilot workload in the cockpit. As we move through this section, keep in mind that a solid understanding of the basic operating principles will help you make better decisions when managing engine performance and responding to any abnormalities that may arise in flight. When we talk about power plant options in general aviation, 2 primary ignition systems come into play: spark ignition and compression ignition. Understanding the difference between these two is fundamental to understanding how your aircraft's engine works. Spark ignition is the traditional design most general aviation pilots are familiar with. It uses a spark plug to ignite a pre-mixed fuel and air mixture inside the cylinder. This technology has been the standard in GA for decades, and its reliability and well-documented maintenance history make it a trusted choice. Compression ignition, on the other hand, works differently. Instead of a spark, it compresses air so intensely that the temperature rises high enough to automatically ignite fuel the moment it's injected. You'll sometimes hear these referred to as jet fuel piston engines because they run on diesel or Jet A fuel, both of which are typically less expensive and more widely available around the world than aviation gasoline. Here's the key takeaway. Despite these differences in how ignition occurs, both engine types share the same fundamental mechanical design: cylindrical combustion chambers, pistons, and a crankshaft that converts the back-and-forth linear motion of the pistons into the rotary motion needed to drive the propeller. The ignition process is what sets them apart, but the core mechanical principles remain the same. There are 4 primary engine cylinder arrangements used in aircraft, each with distinct characteristics that make them suited to different applications. The radial engine arranges its cylinders in a circular pattern around the crankcase, offering an excellent power-to-weight ratio. This design was widely used during World War II, and some radial engines remain in service today. The inline arrangement places cylinders in a single row, giving the aircraft a small frontal area, but it suffers from a low power-to-weight ratio and is generally limited to 4 to 6 cylinders because cooling the rear cylinders becomes increasingly difficult as more are added. The V-type engine improves on the inline design by producing more horsepower while still maintaining that small frontal area, offering a good balance between power output and aerodynamic efficiency. Finally, the horizontally opposed engine is the most common configuration found in small general aviation aircraft. Its cylinders are mounted flat on either side of the crankcase, resulting in a high power-to-weight ratio, a compact layout, and minimal aerodynamic drag. You will always find an even number of cylinders in this arrangement. As you progress through your training, you will most likely encounter the horizontally opposed engine more than any other type. Reciprocating aircraft engines come in several configurations, and 2 of the most historically and practically significant are the radial and the horizontally opposed designs. The radial engine arranges its cylinders in a circular pattern around a central crankshaft. This design provides an excellent power-to-weight ratio, making it well-suited for larger, high-performance aircraft, and it was widely used in both military and commercial aviation throughout much of the 20th century. The horizontally opposed engine, on the other hand, is the dominant choice for small general aviation aircraft today. In this configuration, cylinders are arranged in 2 banks on opposite sides of the crankshaft, lying flat and facing outward. This layout keeps the engine compact and low profile, which improves streamlining and forward visibility from the cockpit. These engines are typically air-cooled, which simplifies the cooling system and reduces overall weight. As you study these designs, pay close attention to how engine configuration directly influences aircraft performance, maintenance requirements, and overall airframe design. The 4-stroke cycle is the fundamental operating principle behind most aircraft reciprocating engines, and understanding each stroke is essential for any pilot or aviation maintenance technician. The cycle begins with the intake stroke. The intake valve opens and the piston moves downward, creating a low-pressure area that draws the fuel-air mixture into the cylinder. Next is the compression stroke. Both valves are closed as the piston travels back up, compressing the fuel-air mixture into a much smaller space. This compression is critical. It significantly increases the energy released during combustion. The 3rd stroke is the power stroke, and this is where useful work is actually produced. The compressed mixture is ignited, and the rapidly expanding gases force the piston downward with considerable force. This linear motion is converted into rotational movement through the crankshaft, ultimately driving the propeller. Finally, the exhaust stroke clears the cylinder for the next cycle. The exhaust valve opens and the piston moves upward, pushing the burned gases out of the cylinder. It's important to recognize that this entire 4-stroke sequence occurs within just 2 complete revolutions of the crankshaft. In a multi-cylinder engine, these cycles are carefully timed and staggered to produce smooth, continuous power output. When it comes to power plants used in general aviation, understanding the difference between 2-stroke and 4-stroke engines is fundamental. A 2-stroke engine completes all 4 processes: intake, compression, power, and exhaust. within just 2 piston strokes. This design produces a higher power-to-weight ratio, which can be advantageous in certain applications. While older 2-stroke designs had limitations, modern versions incorporating direct fuel injection and pressurized air have made them a much more viable option for aviation use. The 4-stroke engine, however, remains the dominant power plant in general aviation today. In this design, each process, intake, compression, power, and exhaust, occurs in its own dedicated stroke, resulting in smoother, more efficient operation. Spark ignition. 4-stroke engines are what you will most commonly encounter throughout your training and career in general aviation, so developing a thorough understanding of how they operate is essential to becoming a competent and safe pilot. The spark ignition engine is made up of several key components, each serving a distinct and critical function. The cylinder is the heart of the combustion process. It houses the intake and exhaust valves, the spark plugs, and the pistons. This is where the air-fuel mixture enters, gets ignited, and the resulting energy is converted into mechanical motion. Below the cylinders sits the crankcase, which encloses the crankshaft and connecting rods. These components work together to translate the up and down motion of the pistons into the rotational force that ultimately drives the propeller. Finally, the accessory housing is typically found at the rear of the engine and supports the auxiliary systems such as the magnetos, fuel pump, oil pump, and vacuum pump. Understanding how these 3 main sections work together gives you the foundation you need to recognize normal engine operation and identify potential issues during pre-flight and in flight. Diesel and jet-fueled piston engines represent a significant development in general aviation powerplant technology. The story begins with Frank Thielert, who pioneered modern diesel aircraft engine design. His work culminated in March 2001 when Thielert aircraft engines produced the first certified diesel piston engine since World War II, a remarkable milestone for the industry. So why does this matter? These engines run on standard aviation kerosene, or Jet A fuel, which is widely available around the world and typically less expensive than aviation gasoline. This gives operators a significant advantage in terms of fuel accessibility and cost. Combined with higher reliability and lower overall operating costs, these engines present a compelling case for both flight training and private operations. Another key feature is FADEC, Full Authority Digital Engine Control, which is standard on diesel-equipped aircraft. FADEC simplifies engine management by automating many of the power settings the pilot would otherwise have to manage manually. You'll find these engines installed on aircraft like the Diamond DA-40 and the DA-42 Twin Star, and supplemental type certificates are available to install them on popular platforms like the Cessna 172 and Piper PA-28. By 2007, these engines had accumulated over 600,000 flight hours, demonstrating their real-world reliability and growing acceptance across the aviation community. The propeller is not simply a spinning blade. It is a rotating airfoil, and understanding it as such is fundamental to grasping how it functions. Just like a wing, the propeller is subject to induced drag, the possibility of stalling, and all the same aerodynamic principles that govern flight surfaces. Rather than producing lift in the traditional vertical sense, the propeller converts that aerodynamic force into thrust, pulling or pushing the aircraft forward through the air. One of the most important design features of a propeller blade is its twist. The blade is not uniform from root to tip. It is deliberately twisted so that the angle of incidence decreases as you move outward from the hub toward the tip. The hub section has the highest pitch, while the tip has the smallest. The reason for this is straightforward. The tip of the blade travels a much greater distance through the air with each revolution than the hub does, meaning it moves at a significantly higher speed. By reducing the angle of incidence at the tip and increasing it at the hub, the designer ensures that aerodynamic force, and therefore thrust, is produced uniformly along the entire length of the blade. Without this twist, the blade would be highly inefficient and unevenly loaded. One of the most important design features of a propeller blade is its twist, and understanding why that twist exists comes down to basic geometry. When a propeller spins, every point along the blade completes one full rotation in the same amount of time. However, points closer to the tip must travel a much greater distance than points near the hub. This means the tip is moving significantly faster through the air. At 2,500 RPM, a point 60 inches from the hub is traveling at approximately 389 knots, while a point only 20 inches from the hub is moving at a fraction of that speed. If the blade had a constant pitch angle from root to tip, the sections near the tip would be operating at a very different angle of attack than those near the hub, resulting in uneven and inefficient lift production across the blade. By gradually changing the pitch angle along the length of the blade, higher pitch near the hub, lower pitch near the tip, the designer compensates for these speed differences. The result is a more uniform angle of attack across the entire blade, which produces consistent lift and thrust from hub to tip and allows the propeller to operate efficiently. A fixed-pitch propeller is ground-adjusted to a single blade angle that cannot be changed in flight. Because of this, the pilot must choose between two main configurations depending on the intended mission. A climb propeller uses a lower pitch setting, which reduces drag on the blades and allows the engine to turn at higher RPM. This delivers better acceleration and climb performance, but the efficiency drops off once you reach cruise altitude and airspeed. A cruise propeller works the opposite way. The higher pitch setting means the engine turns at lower RPM, which improves fuel efficiency in level flight, but sacrifices some takeoff and climb performance. The important concept to understand is that any fixed-pitch propeller is only truly efficient at one specific combination of airspeed and RPM. Outside of that sweet spot, you are accepting a performance trade-off. Because you cannot vary the pitch in flight, the tachometer becomes your primary instrument for monitoring engine power output. One additional consideration: as you climb to higher altitudes, air density decreases. Even if your tachometer shows the same RPM reading, the engine is actually producing less horsepower because the thinner air reduces the power available to the engine. The tachometer is your primary instrument for monitoring engine and propeller speed, and it displays revolutions per minute calibrated in hundreds. As you scan the instrument, pay close attention to the green arc, which represents the maximum continuous operating range. You should keep your engine operating within this arc during normal flight to ensure longevity and safe performance. One important concept to understand is how altitude affects your RPM readings. As you climb to higher altitudes, the air becomes less dense. That reduced air density means the engine produces less power for a given throttle position, even if the tachometer reads the same RPM. To maintain your desired RPM at altitude, you will need to advance the throttle further than you would at lower elevations. This is a fundamental characteristic of normally aspirated engines, and recognizing this relationship will help you manage engine performance effectively throughout all phases of flight. Building on fixed-pitch designs, the next step in propeller evolution introduced the ability to change blade pitch, first on the ground and eventually in flight. The adjustable pitch propeller allowed mechanics to set blade angle while the engine was not running, offering typically just two positions: low pitch for takeoff and high pitch for cruise. This was the direct forerunner of what became the constant speed propeller. The constant speed propeller is the most efficient type in common use today. A governor automatically adjusts blade angle in flight to maintain whatever RPM the pilot has selected, regardless of changing air loads or flight conditions. This allows the propeller to convert a consistently high percentage of brake horsepower into thrust horsepower across a wide range of power settings and air speeds. Aircraft equipped with a constant speed propeller have two separate controls to manage. The throttle controls the engine's power output, which you monitor on the manifold pressure gauge. The propeller control works through the governor to set your desired RPM. Understanding how these two controls interact is essential. Proper management of both directly affects engine efficiency, performance, and longevity. You'll want to develop good habits around sequencing these controls during climbs, cruise, and descent. The manifold pressure gauge, often referred to as the MAP gauge, measures the absolute pressure of the fuel-air mixture inside the engine's intake manifold. With the engine off, the gauge reads ambient atmospheric pressure, which is approximately 29.92 inches of mercury. Once the engine starts and you move to idle, That reading drops significantly, down to around 12 inches of mercury, because the pistons are creating a strong vacuum in the intake system. Like other engine instruments, the gauge uses color coding to communicate limits at a glance. The green arc represents the normal operating range, and the red radial line marks the upper limit you must not exceed. One important diagnostic use of this gauge is recognizing engine failure. If the engine stops producing power, manifold pressure will rise back toward ambient pressure, giving you an early indication that something has gone wrong. Pay close attention to the correct sequence when changing power settings. When decreasing power, reduce manifold pressure first, then reduce RPM. When increasing power, always increase RPM first, then add manifold pressure. Reversing this order places excessive stress on the engine internals and can cause serious damage. Getting this sequence right every time is a fundamental habit of good engine management. In March 2010, the FAA issued Safety Advisory Bulletin SAIB CE 1021 addressing propeller overspeed events in piston engine aircraft equipped with variable pitch propellers. This bulletin highlights a critical lesson that every pilot operating this type of aircraft should understand. In the incident described, a single-engine aircraft experienced a propeller overspeed at 7,000 feet during cruise flight. The blade pitch mechanism failed to the low pitch stop, which effectively caused the propeller to behave like a fixed-pitch propeller. The pilot, following standard training, established best glide speed at 110 knots, but was unable to reach the nearest airport. Here is the key takeaway from the subsequent performance evaluation. In certain overspeed conditions, flying below the published best glide speed can actually generate more thrust from the windmilling propeller, potentially allowing the aircraft to maintain level flight rather than descend. This is counterintuitive to what most pilots have been taught. The practical implication is this: if you experience a propeller overspeed and altitude permits, experimenting with a lower airspeed may dramatically improve your outcome. However, and this is critical, you should only explore alternative airspeeds when you have sufficient altitude to safely evaluate the results and recover if needed. Never attempt this at low altitude where you have no margin for error. The induction system is responsible for getting the right mixture of air and fuel into the engine's cylinders for combustion. Outside air enters through an intake port on the engine cowling, which typically includes an air filter to keep contaminants out of the engine. There are two main types of induction systems you'll encounter in general aviation aircraft. The first is the carburetor system, which blends fuel and air together inside the carburetor before that mixture travels through the intake manifold, and into the cylinders. Carburetors come in two varieties, float type and pressure type, with the float type being the most common on smaller training aircraft. The second type is the fuel injection system, which mixes fuel and air much closer to the cylinders, or in some designs, injects fuel directly into each cylinder. Fuel injection systems are generally more efficient and notably less susceptible to induction icing compared to carburetor systems. One important safety feature found in both system types is an alternate air source. If the primary air filter becomes clogged, this alternate pathway ensures the engine continues to receive airflow. Depending on the aircraft, this bypass may activate automatically, or it may require a manual selection by the pilot. Always know which type your aircraft uses and how to operate it correctly. In a float-type carburetor, air passes through a venturi, a narrowed section of the intake passage. As air accelerates through this restriction, its pressure drops, and that low pressure draws fuel up through the main jet and into the airstream. The fuel-air mixture then travels through the throttle valve and onto the combustion chambers. Fuel level in the float chamber is maintained by a float connected to a needle valve. As fuel is consumed, the float drops, the needle valve opens, and fuel enters to restore the correct level. The primary disadvantage of the float-type carburetor is its tendency to ice. Two conditions contribute to this: the temperature drop caused by fuel vaporization and the pressure drop through the venturi, both of which can significantly reduce local temperatures, even on a relatively warm day. Ice can form on the throttle valve and venturi throat, restricting airflow and reducing engine power with little warning. This is why carburetor heat is a critical control, and pilots must understand when and how to apply it effectively. Recognizing the conditions favorable to carburetor icing, typically between -10 and +30 degrees Celsius with high humidity, is an essential part of safe engine management. As an aircraft climbs to higher altitudes, the air becomes less dense. However, fuel density remains constant, which means the engine is receiving proportionally more fuel relative to the available oxygen. The result is a progressively richer mixture, and left uncorrected, this leads to engine roughness, spark plug fouling, and a noticeable loss of power. The solution is to use the mixture control to lean the mixture as you climb. By reducing fuel flow, you compensate for the reduced air density and restore the proper fuel-to-air ratio. It's equally important to remember the reverse during descent. As air density increases again, you must enrich the mixture to avoid running too lean, which can cause detonation and dangerous overheating of the engine. For the most precise mixture management, use the exhaust gas temperature gauge, or EGT. This instrument gives you real-time feedback on combustion conditions, allowing you to set the mixture accurately rather than relying on estimation alone. Proper mixture control is not just about performance. It directly affects engine longevity and safety throughout the entire flight. One of the most insidious threats to engine performance is carburetor icing, and understanding it is critical because it can occur under conditions that might seem completely benign. When fuel vaporizes inside the carburetor and the pressure drops through the venturi, the resulting temperature drop can be as dramatic as 60 to 70 degrees Fahrenheit. This means ice can form even when outside air temperatures are as high as 100 degrees Fahrenheit, with relative humidity as low as 50%. The most dangerous conditions are outside air temperatures below 70 degrees Fahrenheit combined with relative humidity above 80%. Conditions you might encounter on a mild, humid day that feels perfectly comfortable in the cockpit. Knowing how to recognize carburetor icing depends on your aircraft's propeller system. In a fixed-pitch propeller aircraft, you'll see an unexplained decrease in engine RPM. In a constant-speed propeller aircraft, the propeller governor compensates to maintain RPM. So instead, you'll notice a gradual decrease in manifold pressure with no corresponding RPM change. If you observe either of these indications and suspect carburetor icing, apply carburetor heat immediately and be prepared for a brief roughness as the ice melts and passes through the engine. One of the most important tools for recognizing carburetor icing risk is the carburetor icing potential chart. This chart maps out combinations of outside air temperature and relative humidity that create favorable conditions for ice to form inside the carburetor. The highest risk zone falls roughly between 20 and 70 degrees Fahrenheit when relative humidity is above 80%. Within this range, icing is not just possible, it is likely, and pilots should apply carburetor heat proactively rather than waiting for symptoms to appear. However, icing is possible across a much wider range of conditions than the high-risk zone alone, so you should never assume you're safe simply because conditions fall outside that core area. There is also a critical caution to keep in mind. Carburetor icing can occur under conditions that are not even depicted on this chart at all. Factors such as engine power setting, fuel type, and airframe-specific characteristics can all influence icing susceptibility in ways this chart does not fully capture. Use the chart as a guide, but treat carburetor icing awareness as an ongoing habit, rather than a checklist item you check off once during pre-flight. Carburetor heat is one of the pilot's primary defenses against carburetor icing, and understanding how to use it correctly can be the difference between a routine flight and an engine failure. Its purpose is straightforward. It preheats incoming air before it reaches the carburetor, keeping the fuel-air mixture above freezing temperatures. It can also melt ice that has already formed, and serves as an alternate air source if the main intake filter becomes blocked. When you suspect icing, apply full carburetor heat immediately. This is important. Partial heat can actually make the situation worse by warming the air just enough to increase moisture without fully melting the ice. Leave carb heat on until you're confident all ice has cleared. Be aware of the power penalty. Heated air is less dense, so you can expect up to a 15% reduction in engine power. For this reason, carburetor heat should never be used during takeoff or any phase requiring full power. Here's what to expect when you apply carb heat with ice present. You'll initially see a drop in RPM, followed by a gradual increase as the ice melts. That temporary drop is normal. Do not pull the heat back during this period. Stick with it and let the heat do its job. Always check carburetor heat operation during your engine run-up before flight. The carburetor air temperature gauge is a critical instrument for detecting and preventing carburetor ice. It is calibrated in degrees Celsius and features a yellow arc spanning from -15 degrees to +5 degrees Celsius. This yellow arc represents the range where carburetor icing is most likely to occur. A red radial line marks the maximum permissible inlet temperature, and you must never allow the indicator to remain within the yellow arc when icing conditions are present. If you notice the needle entering that yellow arc, apply carburetor heat immediately to raise the temperature out of the danger zone. The outside air temperature gauge, or OAT, is a standard instrument found on most aircraft and is calibrated in both degrees Celsius and Fahrenheit. It serves two important purposes. First, it allows you to calculate true airspeed, since air density changes with temperature and affects your indicated versus actual speed through the air. Second, it helps you assess the potential for icing conditions before they develop inside the induction system. By monitoring both the OAT and the carburetor air temperature gauge together, you gain a much more complete picture of your icing risk and can take proactive steps to protect engine performance. Fuel injection systems offer several significant advantages over carburetor-based induction systems, and understanding both sides of the equation is essential for safe operations. On the advantage side, fuel injection virtually eliminates evaporative icing since there is no venturi or throttle body where fuel evaporation can cause temperature drops. Fuel distribution to each cylinder is more precise and consistent, which improves engine efficiency and performance. Throttle response is noticeably crisper, mixture control is more accurate, and cold weather starting is generally more reliable when proper procedures are followed. However, fuel injection systems do come with their own set of challenges. A hot engine can be difficult to start because residual heat causes fuel in the lines to vaporize, making it hard to establish proper fuel flow. This same issue, known as vapor lock, can affect ground operations on hot days. Perhaps most critically, if the engine experiences fuel starvation and stops running, restarting it requires deliberate steps to reprime the system, something that demands thorough knowledge of your aircraft's specific procedures before it ever becomes an in-flight emergency. Knowing these limitations ahead of time allows you to anticipate problems and respond correctly, rather than being caught off guard. Forced induction systems are a critical development in aviation engine technology, allowing aircraft to maintain power output at altitudes where the air is too thin for a naturally aspirated engine to perform effectively. There are two primary types you need to understand. The supercharger is a compressor driven directly by the engine itself, typically through a gear system. It can operate at 1 speed, 2 speeds, or variable speeds depending on the design, and it's capable of boosting manifold air pressure above 30 inches of mercury. However, because the supercharger draws its power from the engine, it consumes a portion of the very power it's trying to supplement, which is its main drawback. The turbo supercharger, commonly called a turbocharger, takes a more efficient approach. Instead of tapping into engine power, it's driven by exhaust gases, energy that would otherwise be expelled and wasted. This makes it significantly more efficient than a gear-driven supercharger. A properly functioning turbocharger can maintain rated sea-level horsepower all the way up to the engine's critical altitude, which is the highest altitude at which the system can still hold full-rated manifold pressure. Understanding the difference between these two systems, particularly how each derives its power and what limitations each carries, is essential for operating turbocharged or supercharged aircraft correctly and safely. The turbocharger is a key component in many high-performance aircraft engines, and understanding how it works is essential for safe operation. At its core, the turbocharger consists of two main elements connected by a common shaft, a turbine wheel and a compressor impeller. Exhaust gases exiting the engine flow through the turbine, causing it to spin at extremely high speeds. That spinning motion drives the compressor impeller, which draws in outside air, compresses it, and forces it into the induction system at a higher pressure than would be possible at altitude. Controlling the amount of boost the turbocharger produces is the job of the wastegate. Think of it as a bypass valve in the exhaust path. When the wastegate is closed, more exhaust gas is directed through the turbine, increasing its speed and boosting compressor output. As the wastegate opens, exhaust bypasses the turbine, reducing boost pressure. This allows precise regulation of manifold pressure throughout the flight envelope. One important consideration is heat. Compressing air raises its temperature significantly, and hotter air is less dense and more prone to causing detonation. That is where the intercooler comes in. By cooling the compressed air before it reaches the fuel metering device, the intercooler improves charge density and reduces the risk of detonation, helping protect the engine under high-power conditions. When operating a turbocharged engine, there are three key considerations every pilot must understand to protect the engine and maintain safe performance. First, overboost risk. If the wastegate remains closed after a descent, manifold pressure can climb beyond the engine's limits, causing serious damage. Cold oil at startup is another overboost trigger. Always advance the throttle gradually until the engine reaches normal operating temperatures. Second, bearing lubrication. The turbocharger's turbine and impeller can spin in excess of 80,000 RPM under extremely high temperatures, so adequate oil pressure and temperature are essential before applying high throttle settings. Just as important is the shutdown procedure. Always allow the turbocharger time to cool down before shutting off the engine. Failing to do so can cause oil to carbonize inside the bearings, leading to premature wear and potential failure. Third, critical altitude. This is the maximum altitude at which a turbocharged engine can still produce its rated horsepower. If you notice manifold pressure dropping below the specified value before reaching that critical altitude, this is a sign the system is not performing correctly and should be inspected by an aviation maintenance technician before further flight. Understanding these considerations helps you operate the turbocharger safely and extend the life of the engine. The ignition system is responsible for delivering the spark that ignites the fuel-air mixture inside the engine cylinders. Understanding its components and how they work together is essential for any pilot. The system consists of four main components: magnetos, spark plugs, high-tension leads, and the ignition switch. Each plays a critical role in ensuring reliable engine operation. The magneto is perhaps the most important component to understand. Unlike most aircraft electrical systems, the magneto uses a permanent magnet to generate its own electrical current. This means it operates completely independently of the aircraft's battery and electrical system. As long as the crankshaft is rotating, the magneto is producing electricity and delivering sparks to the cylinders. This independence is a significant safety feature. If the aircraft's main electrical system fails, the engine will continue to run without interruption because the magnetos require no external power source. Most aircraft engines are equipped with two separate magneto systems and two spark plugs per cylinder. This dual redundancy design ensures that if one magneto fails, the engine continues to operate on the other, maintaining power and allowing the pilot to land safely. Most certificated aircraft are equipped with a dual ignition system, meaning two completely independent magnetos, two separate sets of ignition wires, and two spark plugs in each cylinder. The reason for this redundancy is simple: safety and reliability. If one magneto fails in flight, the other continues to operate completely unaffected, and the engine keeps running with only a slight reduction in power output. The ignition switch gives you control over this system with 5 positions: off, R for right magneto only, L for left magneto only, both for normal operation, and start. During your run-up, you'll test each magneto individually by switching from both to R and then to L. A small RPM drop is expected and tells you each magneto is working correctly. However, an excessive drop indicates a problem, and no drop at all means the magneto is not being properly grounded. Either way, do not fly. One critical safety point to remember: even with the ignition switch in the off position, the engine can still fire if the P-lead ground wire is broken or disconnected. If fuel is present in a cylinder and someone moves the propeller, the engine can kick. Always treat any propeller as if the engine could start. If you need to stop a runaway engine and the switch is unresponsive, move the mixture to idle cutoff to stop fuel flow immediately. Normal combustion is the ideal scenario. The spark plug fires and the flame front travels smoothly and predictably outward through the fuel-air mixture. This produces a controlled progressive pressure rise that pushes the piston down at exactly the right moment in the power stroke, delivering maximum efficiency and power. Detonation is something you absolutely want to avoid. Instead of a smooth burn, the remaining unburned mixture explodes spontaneously and violently. This creates a sudden, uncontrolled spike in cylinder pressure and temperature that can rapidly destroy engine components. Common causes include using the wrong fuel grade, running high manifold pressure with low RPM, or operating with an excessively lean mixture. If you hear a knocking or pinging sound from the engine, detonation is a likely culprit. Pre-ignition occurs when the fuel-air mixture ignites before the spark plug even fires. This is typically caused by a hot spot inside the cylinder, such as a carbon deposit or a cracked spark plug, that becomes hot enough to act as an ignition source on its own. Pre-ignition can cause significant power loss and dangerously high cylinder temperatures. It can also lead to detonation, making the two conditions particularly harmful when they occur together. Recognizing and understanding both of these abnormal combustion events is essential for protecting your engine and responding correctly in flight. Full authority. Digital engine control, or FADEC, represents a significant advancement in how modern aircraft engines are managed. Rather than relying on the pilot to manually adjust mixture, ignition timing, and other engine parameters, FADEC uses a digital computer combined with sensors throughout the engine to handle all of this automatically. It continuously monitors cylinder speed, temperature, and pressure, then calculates and delivers the ideal fuel pulse while adjusting ignition timing in real time for optimal performance. From a pilot workload perspective, FADEC dramatically simplifies engine management. It eliminates the need for magnetos, carburetor heat, mixture controls, and engine priming. Instead of managing multiple controls, you work with a single throttle lever that uses detents for start, idle, cruise, and maximum power. The system takes care of everything else behind the scenes. Reliability is addressed through redundancy. FADEC uses two separate identical digital channels, and either channel alone can provide full engine and propeller function without limitation. However, it's critical to understand that a complete FADEC failure could result in total loss of thrust. Because of this, backup power to the FADEC system is essential and must be maintained. Always verify your backup power source is functioning as part of your pre-flight and normal operating procedures. Turbine engines are a fundamental part of aviation, and understanding their basic layout is essential. All turbine engines share the same core components: an air inlet, a compressor, combustion chambers, a turbine section, and an exhaust. The core principle is straightforward. Thrust or shaft power is generated by accelerating air through the engine. Compared to piston engines, turbines offer smoother operation, excellent power-to-weight ratios, and run on widely available jet fuel. Now, there are four main types you need to know. The turbojet is the purest form. All thrust comes directly from the jet exhaust. However, it has limited range and endurance, and throttle response can be sluggish at low speeds. The turboprop uses the turbine to drive a propeller through a reduction gearbox. It performs best between 250 and 400 miles per hour at altitudes between 18,000 and 30,000 feet, making it ideal for regional and cargo operations. The turbofan adds a large fan that bypasses air around the core. This bypass air contributes to thrust, helps cool the engine, and significantly reduces noise. It offers the best cruise efficiency and is the dominant power plant on modern commercial aircraft. Finally, the turboshaft delivers power to a rotating shaft rather than producing direct thrust. This design is used extensively in helicopters and auxiliary power units. Let's take a look at two foundational types of turbine engines, the turbojet and the turboprop, and understand how they differ in design, efficiency, and application. The turbojet is the simplest turbine engine configuration. Air enters the inlet, gets compressed, is mixed with fuel and ignited in the combustion chamber, and is then forced out through the turbine and exhaust nozzle at high velocity. That high-velocity exhaust is what generates thrust. Because of this design, the turbojet performs best at high speeds and high altitudes, but it burns a significant amount of fuel at lower speeds, making it inefficient for slower flight regimes. You'll find it primarily in military jets and early commercial airliners. The turboprop takes a different approach. It uses the same gas turbine core, but instead of relying primarily on exhaust thrust, it channels most of that energy through a reduction gearbox to drive a propeller. Roughly 90% of the thrust comes from the propeller, with only about 10% from jet exhaust. This makes the turboprop highly efficient at lower speeds and altitudes, generally below 30,000 feet and 400 knots, which is why it's widely used in regional airliners, cargo aircraft, and utility operations. Understanding these differences helps you recognize why aircraft are matched to specific engine types based on their intended mission and operating environment. The turbofan and turboshaft represent two important variations of the gas turbine engine, each optimized for very different applications. The turbofan adds a large fan at the front of the engine core. This fan moves a substantial volume of air around the core, and that bypassed air generates the majority of thrust at subsonic speeds. We measure this using the bypass ratio, the mass airflow through the fan divided by the mass airflow through the core. High bypass turbofans, with ratios of 5:1 or greater, deliver excellent fuel efficiency and are the standard power plant for commercial airliners. Military aircraft often use low bypass designs to better balance outright speed with efficiency. The turboshaft takes a fundamentally different approach. Instead of producing thrust, the turbine extracts nearly all available energy from the exhaust gases to drive a rotating shaft. That shaft then powers a rotor, transmission, or other mechanical load. Jet thrust is minimal. Virtually all usable power comes out through the shaft, measured in shaft horsepower. Helicopters are the most common application, along with auxiliary power units and hovercraft. The core distinction between these two engines comes down to their primary output. Turbofans are optimized to produce thrust for high-speed subsonic flight. Turboshafts are optimized to deliver mechanical shaft power across a range of operating speeds. Understanding this difference is essential when evaluating power plant selection for any given aircraft or application. Turbine engines rely on a specialized set of instruments to monitor performance and ensure safe operation. Let's walk through the key gauges you need to understand. The engine pressure ratio gauge, or EPR, measures the ratio of turbine discharge pressure to compressor inlet pressure. This ratio gives pilots a direct indication of the thrust being produced by turbojet and turbofan engines, making it a primary power instrument in those aircraft. The exhaust gas temperature gauge monitors the heat levels within the turbine section. You may see this referenced under several different names depending on where the temperature sensor is located, including TT, TOT, ITT, or TGT. Regardless of the label, the purpose is the same: protecting the turbine from exceeding its thermal limits. On turboprop and turboshaft engines, the torque meter measures the actual power being delivered to the propeller or rotor shaft. It may be calibrated in percentage units, foot-pounds, or SAI depending on the aircraft. Finally, the N1 and N2 indicators display compressor spool speeds. N1 represents the low-pressure compressor, while N2 represents the high-pressure compressor. Both are expressed as a percentage of the engine's design RPM. Together, these instruments give a comprehensive picture of turbine engine health and power output. Let's look at some of the key operational hazards associated with turbine engines, hazards that every pilot operating turbine-powered aircraft needs to understand thoroughly. Foreign object damage, or FOD, occurs when debris is ingested into the engine intake. Even small objects can cause serious damage to compressor blades and turbine components. Prevention is always the priority. Thorough visual inspections before flight, along with vortex dissipators and intake screens where applicable, are your primary defenses. Hot starts and hung starts are two distinct but related starting hazards. A hot start occurs when exhaust gas temperature exceeds safe limits, typically due to excess fuel or insufficient rotor speed during the start sequence. A hung start means the engine fails to accelerate to idle RPM. Both conditions require you to abort the start immediately and have maintenance personnel inspect the engine before any further operation. Compressor stall happens when compressor blade angle of attack exceeds its critical angle, causing airflow disruption or reversal. You may notice RPM fluctuations, rising EGT, and audible banging or popping. Recovery involves reducing power, lowering angle of attack, and increasing airspeed to restore normal airflow. Finally, a flameout is an unintended engine flameout. Combustion simply stops. Causes include an excessively rich mixture, low fuel pressure, or fuel interruption. If you experience a flameout, follow your AFM or POH emergency procedures precisely for an air start attempt. When comparing engines types across the speed spectrum, each has a performance range where it excels. At low speeds, the reciprocating engine outperforms all other engine types, making it the preferred choice for slower aircraft. As speed increases, the turboprop takes over, outperforming the turbofan in that lower speed range. Moving into higher speeds, the turbofan surpasses both the reciprocating engine and turboprop, making it the dominant choice for commercial airliners and many military aircraft. At the extreme end of the speed range, the turbojet achieves the highest maximum speed of all engine types. A critical concept to understand here is how maximum speed is determined for each engine. It occurs at the point where that engine's net thrust curve intersects the aircraft's drag curve. Beyond that intersection point, drag exceeds available thrust and the aircraft cannot accelerate further. This comparison reinforces why engine selection is directly tied to the intended operational speed range of the aircraft. The engine oil system plays a critical role in keeping the engine running safely and efficiently. Oil does much more than simply lubricate moving parts. It reduces friction between metal surfaces, which in turn lowers heat generated by that friction. It also helps remove heat directly from the cylinders, seals the small gaps between the cylinder walls and pistons to maintain compression, and carries contaminants away from critical components to prevent wear and damage. There are two primary types of oil systems used in aircraft engines. In a wet sump system, the oil is stored in a sump that is built directly into the engine. A main pump draws oil from that sump and circulates it throughout the engine. This design is common in smaller, lighter aircraft engines due to its simplicity. In a dry sump system, the oil is stored in a separate external tank rather than within the engine itself. Scavenge pumps continuously return used oil from the engine back to that external tank. This arrangement allows for a significantly greater volume of oil, making it well suited for larger, more powerful engines with higher lubrication demands. Understanding which system is installed on your aircraft is essential for proper pre-flight checks and oil level monitoring. The oil system gauges provide essential information about engine health and must be understood thoroughly by every pilot. Let's walk through each one. The oil pressure gauge gives you a direct reading in pounds per square inch and is one of the most critical instruments in the cockpit. Green indicates normal operating range, while red markings show you the minimum and maximum limits. During engine start, you should see oil pressure begin to rise promptly. If you do not see an indication of oil pressure within a few seconds of startup, shut the engine down immediately to prevent serious damage. The oil temperature gauge responds more slowly than pressure, so changes can be gradual. Green is your normal operating range, and the red line marks the maximum allowable temperature. If you notice elevated oil temperature, it could point to a plugged oil line, low oil quantity, or a blocked oil cooler, all conditions requiring immediate attention. Finally, the oil dipstick is your hands-on check during every pre-flight inspection. Always verify oil quantity before flight and add oil if the level falls below the manufacturer's recommended minimum. Be sure to consult your aircraft flight manual or pilot's operating handbook for the correct oil type, viscosity weight, and acceptable quantity range for your specific aircraft. Using the wrong oil or operating outside approved limits can compromise engine reliability. Most small aircraft engines rely on air cooling rather than liquid cooling systems. Outside air enters through openings in the engine cowling, where internal baffles direct that airflow across the cylinder cooling fins, and then it exits through openings in the lower rear portion of the cowling. This design is simple and effective, but it depends heavily on proper airflow management during flight operations. Two specific situations can compromise cooling effectiveness. During a high-speed descent, rapid airflow over the cylinders can cause shock cooling, where the engine temperature drops too quickly and creates harmful thermal stress. On the opposite end, operating at high power settings with low airspeed, such as during a steep climb, reduces the volume of cooling air moving through the cowling, which can allow temperatures to rise dangerously. Understanding the consequences of operating above design temperature is critical. Overheating can lead to a serious cascade of problems, including loss of engine power, excessive oil consumption, detonation, scored cylinder walls, damaged pistons and rings, and burned valves. These are not minor issues. They can lead to catastrophic engine failure. Always monitor your cylinder head and oil temperatures and adjust your power settings and airspeed to keep the engine operating within its designed thermal limits. The cylinder head temperature gauge, or CHT gauge, gives you a direct and immediate reading of how hot your engine cylinders are running. It's calibrated in either degrees Celsius or Fahrenheit depending on the aircraft. And like other engine instruments, it uses a green arc to indicate the normal operating range and a red line to mark the maximum allowable temperature you must never exceed. Managing cylinder head temperature is an essential part of engine management. If your CHT is climbing too high, you have several tools available. You can increase airspeed to move more cooling air over the engine, enrich the fuel-air mixture to help carry heat away from the cylinders, or reduce power to lower the heat being generated. Many aircraft are also equipped with cowl flaps, hinged covers located over the hot air exit on the engine cowling. Opening the cowl flaps increases airflow through the engine compartment, which brings temperatures down. Closing them restricts that airflow, which is useful during cold weather operations to help the engine reach and maintain its proper operating temperature. Understanding how to use these controls together gives you precise command over your engine's thermal health throughout all phases of flight. Aircraft fuel systems are designed around one fundamental principle: getting fuel from the tank to the engine reliably. The specific method depends largely on the aircraft's configuration. On high-wing aircraft, a gravity feed system is used. Because the fuel tanks are located in the wings above the carburetor, gravity alone moves the fuel downward through the system. There are no pumps required, which makes this design exceptionally simple and dependable. Low-wing aircraft, however, present a different challenge. Since the fuel tanks sit below the engine, gravity works against you. These aircraft use a fuel pump system consisting of two components: an engine-driven main pump that operates whenever the engine is running, and an electrically driven auxiliary pump, often called the boost pump. The boost pump is controlled from the flight deck and serves two important purposes. It primes the system during engine start, and it provides backup fuel pressure if the main pump ever fails. You should always consult your aircraft's pilot operating handbook for the specific procedures regarding when to use the boost pump, as requirements vary by aircraft model. Understanding which system your aircraft uses is a fundamental part of pre-flight planning and safe fuel management. The fuel system has several critical components every pilot must understand thoroughly. Starting with the fuel selector valve, most light aircraft have positions for left, right, both, and off. As a general rule, you should always use the both position for takeoff and landing. This ensures maximum fuel availability during the most critical phases of flight. The left and right positions may be used for fuel balancing in level flight, but always check your aircraft's specific procedures, as some aircraft restrict when single tank selection is permitted. Now, regarding fuel gauges, this is important. Regulations only require fuel quantity gauges to be accurate at the empty reading. That means a gauge showing a quarter tank could be optimistic. Never trust the gauges alone. Always physically verify your fuel quantity with a visual inspection during pre-flight. Use a calibrated fuel stick if necessary. Finally, the fuel strainer, or sump, collects water and sediment that can enter your fuel system. You must drain the strainer before every flight and inspect the sample carefully for contamination. Water is denser than aviation fuel and will settle to the bottom. In cold weather, water in the fuel system can freeze and block fuel flow. In warm weather, it can be carried directly into the carburetor. Either scenario can result in engine failure. Do not skip this step. Aviation fuel comes in several grades, and knowing the difference between them is critical for safe operations. Each grade is color-coded to help you quickly identify the correct fuel during servicing. Avgas 80 is dyed red and is designed for lower compression engines. Avgas 100 is green and is used in high compression engines. Avgas 100, low lead, commonly called 100LL, is blue and delivers the same performance as Avgas 100s, but with a reduced lead content. It is by far the most widely available aviation gasoline today. Jet A is colorless or straw-colored and is strictly for turbine engines. There are two rules you must never violate. First, never use a lower grade than what your aircraft requires. Using an inferior fuel in a high-compression engine can cause detonation, which can destroy an engine rapidly and without warning. Second, never use automobile gasoline in an aircraft unless that specific aircraft holds an FAA-issued Supplemental Type Certificate, or STC, authorizing its use. Auto fuel lacks the consistency and standards required for aviation. If the correct grade is simply unavailable, you may use the next higher grade as a temporary measure, but always consult the pilot's operating handbook and return to the approved grade as soon as possible. Fuel contamination is one of the most serious and preventable causes of engine failure in aviation, so understanding how it occurs and how to guard against it is essential for every pilot. Contamination typically results from inadequate pre-flight inspections, fuel that has not been properly filtered, partially filled tanks where temperature changes allow moisture to condense inside the tank, or a breakdown in routine maintenance procedures. Each of these is avoidable with disciplined habits. Before every flight, you must drain the fuel strainer and each tank sump into a transparent container and carefully examine what comes out. If the fuel appears cloudy, or if you see a clear layer settled at the bottom of the container, that indicates water is present. Do not take off under any circumstances until the issue is resolved and clean fuel is confirmed. Static electricity is an equally serious hazard during refueling. Aviation fuel produces highly flammable vapors, and even a small static discharge can trigger ignition. Before you remove the fuel cap, bond the aircraft to the refueling nozzle. The fuel truck must also be grounded before the nozzle makes contact with the aircraft. This bonding process equalizes any static differential charge between surfaces, eliminating the risk of a spark. These steps are not optional. They are standard safety protocol and must be followed every single time you refuel. Most aircraft are equipped with either a 14-volt or 28-volt direct current electrical system. The primary source of electrical power comes from engine-driven alternators or generators, which supply current to the aircraft's electrical components while simultaneously keeping the battery charged. Alternators are generally preferred over generators in modern aircraft, and there's a good reason for that. A generator requires relatively high engine speeds to produce adequate electrical output, whereas an alternator can generate sufficient current even at low engine RPM, including during taxi and ground operations. Alternators work by producing alternating current internally, which is then converted to the direct current the aircraft's systems require. This makes them more reliable and efficient across a wider range of operating conditions. Understanding your aircraft's electrical system is essential because nearly every critical system on board, from avionics to lighting to fuel pumps, depends on it functioning properly. Always be familiar with the electrical system specific to the aircraft you're flying. The aircraft electrical system relies on several key components working together to provide reliable power. Let's walk through each one. The master switch is a split rocker design. The left half controls the alternator, and the right half controls the battery. The bus bar serves as a common terminal that connects the electrical system to all equipment drawing electrical power on the aircraft. For monitoring, you have two primary instruments. The ammeter is zero-centered. A positive deflection means the battery is being charged by the alternator. A negative deflection means the system is drawing power directly from the battery. If you see a full-scale negative reading, that's a strong indication of an alternator malfunction and requires immediate attention. Some aircraft use a load meter instead, which shows the percentage of the alternator's total generating capacity currently in use. To protect the system from overloads, fuses and circuit breakers are installed throughout the aircraft. Always carry spare fuses of the correct amperage. Substituting the wrong amperage fuse can create a fire hazard or leave a circuit unprotected. Finally, the voltage regulator automatically stabilizes the output from the generator or alternator, ensuring a consistent voltage level that keeps the battery properly charged during flight. Hydraulic systems are a critical part of aircraft operation, and understanding their basic function is essential for any pilot or aviation technician. On small aircraft, hydraulic systems are commonly used to operate wheel brakes, retractable landing gear, and constant-speed propellers. As aircraft grow larger and more complex, these systems take on even greater responsibility, controlling primary flight surfaces, flaps, and spoilers. Every hydraulic system, regardless of size, is built around the same core components. You have a reservoir that stores the fluid, a pump that pressurizes it, and a filter that keeps contaminants out of the system. A selector valve directs fluid to the appropriate component, a relief valve protects the system from excessive pressure, and an actuator, sometimes called a servo, converts that hydraulic pressure into mechanical movement. The fluid itself is just as important as the hardware. The most common type used in general aviation is a mineral-based hydraulic fluid, which is a petroleum product with a kerosene-like consistency. It's valued for its excellent lubricating properties, which help protect the internal components of the system. Always ensure you're using the correct fluid type specified for your aircraft, as mixing incompatible fluids can cause serious damage to seals and other components. Landing gear configuration is a fundamental aspect of aircraft design that directly affects ground handling, performance, and pilot technique. The most common configuration on modern aircraft is tricycle gear, where the nose wheel sits at the front. This setup places the center of gravity forward of the main wheels, which gives the aircraft natural directional stability on the ground. It allows for more forceful braking without the risk of nosing over, provides better forward visibility during taxi and rollout, and virtually eliminates the tendency to ground loop, a dangerous, uncontrolled swerving that can occur on landing. Tailwheel aircraft, sometimes called conventional gear, place the third wheel at the rear. This design offers better ground clearance for larger propellers and performs well on unimproved or rough surfaces. However, because the center of gravity sits behind the main gear, the aircraft is inherently less stable directionally on the ground. Pilots transitioning to tailwheel aircraft must complete specific training and a logbook endorsement before acting as pilot in command. Finally, landing gear can be either fixed or retractable. Fixed gear is mechanically simple, requires less maintenance, and is always ready. But it creates parasite drag in flight. Retractable gear retracts into the airframe to reduce drag and improve cruise speed, but it introduces additional system complexity, maintenance requirements, and the critical responsibility of ensuring the gear is down before landing. Aircraft are pressurized to make high-altitude flight comfortable and safe for passengers and crew. At cruise altitudes, the outside air is far too thin to breathe, so the pressurization system maintains a cabin environment equivalent to roughly 8,000 feet, an altitude where the human body can function normally without supplemental oxygen. The way pressurization is achieved depends on the type of aircraft. In turbine-powered aircraft, bleed air is tapped directly from the engine compressor stages and routed into the cabin. In piston-powered aircraft, pressurization may be accomplished using air from the turbocharger, often passed through a sonic venturi to regulate flow. Regardless of the source, the key to controlling cabin pressure is the outflow valve. This valve manages how quickly air exits the aircraft, and by varying that exit rate, the system maintains the desired cabin altitude throughout the flight. Think of it as a balance. Air continuously enters the cabin, and the outflow valve precisely controls how much escapes to hold pressure steady. Understanding this fundamental relationship between air input and the outflow valve is essential for grasping how pressurization systems are monitored and managed by the flight crew. There are two types of decompression you need to understand, and both carry serious risks. The first is explosive decompression, where cabin pressure changes faster than your lungs can equalize, in less than half a second. This is potentially dangerous because it can cause lung damage, and it's typically accompanied by a loud noise, a sudden fog from moisture condensation, and flying debris throughout the cockpit or cabin. The second type is rapid decompression, which is less violent but still critical. In this case, your lungs decompress faster than the cabin itself. Importantly, rapid decompression reduces your effective performance time by 1/3 to 1/4, which means you have significantly less time to respond than you might expect. Your oxygen mask must be donned immediately. Do not delay. Regardless of the type, the primary danger of any decompression event is hypoxia, and a rapid descent is essential. If you're operating at 35,000 feet or above, you must already be wearing your oxygen mask and have it selected to 100% oxygen. Beyond hypoxia, structural damage associated with decompression can also expose occupants to violent wind blasts and extreme cold temperatures, adding additional threats to an already dangerous situation. Know your emergency procedures before you need them. Federal aviation regulations establish clear thresholds for supplemental oxygen use, and as a flight crew member, you must know these altitudes without hesitation. Between 12,500 and 14,000 feet cabin altitude, regulations require flight crew to use supplemental oxygen if the aircraft operates at that altitude for more than 30 minutes. Once you exceed 14,000 feet cabin altitude, that grace period disappears entirely. Supplemental oxygen use becomes immediate and mandatory for all flight crew. At 15,000 feet, the requirement extends to every occupant on board, not just the crew. Beyond regulatory minimums, best practice encourages pilots to use supplemental oxygen above 10,000 feet during daylight operations and above 5,000 feet at night, since night vision is particularly sensitive to even mild hypoxia. Aircraft oxygen systems are high-pressure systems, with oxygen stored between 1,800 and 2,200 pounds per square inch. So proper handling and system awareness are essential. Understanding these thresholds is not just a regulatory requirement. It is a critical safety discipline that protects both you and everyone on board from the insidious and often unrecognized effects of hypoxia. There are 4 primary types of oxygen systems used in aviation, and understanding how each one works is essential for safe operation at altitude. The diluter demand system supplies oxygen only when the user inhales, and its automix lever automatically blends cabin air with oxygen based on altitude. This system is approved for use up to 40,000 feet. Above 34,000 feet, the pressure demand system takes over, delivering oxygen under positive pressure, which actually forces oxygen into the lungs and makes it safe for operations above 40,000 feet. For passengers, continuous flow is the most common system. It flows oxygen constantly, and the reservoir bag collects oxygen during exhalation, so a higher concentration is available with each breath. Finally, the pulse demand system is the most efficient, delivering oxygen only during inhalation and reducing consumption by 50 to 85% compared to continuous flow, thanks to its built-in altitude compensating barometer. Regardless of which system you are working with, 2 safety rules are absolute. Never allow oil, grease, or any petroleum-based product anywhere near oxygen equipment, and smoking is strictly prohibited whenever oxygen equipment is in use. Oxygen under pressure and any ignition source is an extremely dangerous combination. Let's talk about 2 important aspects of oxygen systems: the pulse oximeter and the critical safety rules for servicing oxygen equipment. A pulse oximeter is a small, non-invasive device that measures both blood oxygen saturation and heart rate. It clips onto a finger and gives you an accurate reading within 1% of a directly measured blood oxygen level. Above 12,500 feet, where hypoxia becomes a real concern, this tool becomes extremely valuable. It gives you objective data about your physiological state, something your own senses can't always reliably provide when oxygen levels are dropping. When it comes to servicing oxygen systems, safety is non-negotiable. Oxygen reacts violently with petroleum-based products, so all servicing must be done outdoors, never inside a hangar. Before you touch any equipment, wash your hands thoroughly and remove all traces of oil and grease. Your clothing and tools must also be completely oil-free. Fixed oxygen installations require 2 persons present during servicing. You must never service an oxygen system while fueling operations are underway, and passengers must not be aboard the aircraft during the process. These rules exist because oxygen under pressure, combined with any hydrocarbon contamination, can cause a catastrophic fire or explosion. There are no shortcuts here. Understanding the difference between anti-ice and de-ice systems is fundamental to operating safely in cold weather environments. Anti-ice systems are designed to prevent ice from forming in the first place. Because they work proactively, they must be activated before you enter icing conditions. Common examples include thermal systems that use hot bleed air or electric heating elements like the thermowing foil, alcohol-based weeping wing systems that coat the surface to prevent ice adhesion, and heated pitot and static ports. De-ice systems, by contrast, are reactive. They remove ice after it has already formed. The most common example on general aviation aircraft is the inflatable rubber boot. A pneumatic pump inflates the boots along the leading edges, cracking and shedding accumulated ice. An important point here: modern boots should be cycled as soon as you observe ice accumulation. The old concern about ice bridging has been debunked with modern boot designs, so don't wait for heavy accumulation before cycling them. Here is the most critical takeaway for most of you. The majority of light general aviation aircraft have nothing more than a heated pitot tube and are not certified for flight in icing conditions. If you inadvertently encounter icing, your only approved course of action is to exit those conditions immediately. Do not attempt to continue flight hoping conditions will improve. De-icing boots are one of the most common ice protection systems you'll encounter on general aviation and regional turboprop aircraft. These rubber sheets are bonded directly to the leading edges of the wings and tail surfaces, and they work by physically breaking ice apart rather than preventing it from forming in the first place. Here's how the system works. As ice accumulates on the leading edge, you allow it to build to a sufficient thickness, typically 1/4 to 1/2 inch, before activating the boots. The engine-driven pneumatic pump, or bleed air on turboprop aircraft, inflates the boots outward, cracking and shedding the accumulated ice. Activating too early before adequate ice has built up can cause the ice to conform around the inflated boot, a condition known as ice bridging, which reduces the system's effectiveness. Boots can be cycled manually as a single operation or set to inflate and deflate automatically at timed intervals. During normal operation, always monitor your suction gauge and pneumatic pressure gauge to confirm the system is functioning within normal parameters. And critically, never skip a thorough pre-flight inspection of the boots themselves. Look for cracks, tears, or areas that have separated from the leading edge. A damaged boot won't inflate properly and could leave you without effective ice protection when you need it most. When it comes to windscreen anti-ice, there are 2 common methods. The first uses alcohol directed onto the windscreen surface, and the second uses embedded electrical wires or conductive material to prevent ice formation. An important operational note here: these systems should only be activated in flight. Using them on the ground can cause the windscreen to overheat and sustain damage. If your aircraft uses electrically heated windscreen anti-ice, be aware that the electrical current can introduce compass deviation errors of up to 40 degrees, so always cross-check your heading with other navigation references. For propeller anti-ice, alcohol can be discharged from nozzles at the blade root, where centrifugal force then carries it along the leading edge. Some aircraft instead use electrically heated propeller boots, which have both inboard and outboard heating sections. Monitor the prop anti-ice ammeter closely. If one section is heating unevenly, it can produce severe vibration, which is your warning that something is wrong. Beyond these systems, other components such as pitot and static ports, fuel vents, Stall warning sensors and optional installed equipment may also be electrically heated. Never assume these systems are operating correctly without verification. Always consult your AFM or POH and confirm all anti-ice systems are checked and functional before entering any known or forecast icing conditions. As we wrap up Chapter 7, let's reinforce the essential takeaways that every pilot and maintenance-conscious aviator needs to carry forward. Aircraft systems knowledge isn't just academic. It directly impacts the safety of every flight. Always treat the AFM and POH as your primary reference, because system specifications vary significantly from one aircraft to another. For the power plant, know your engine type, understand the ignition system, and never compromise on fuel grade. Continuous monitoring of cylinder head temperature, oil pressure, and oil temperature gives you early warning of developing problems. On induction, don't wait for a rough engine to suspect carburetor ice. Recognize the conditions that create it and apply full carb heat proactively. Manage your mixture appropriately as altitude increases. For fuel, visual verification is non-negotiable. Drain every sump before every flight and confirm you have the correct fuel grade on board. Regarding pressurization and oxygen, know how to recognize and respond to decompression events and use supplemental oxygen earlier than regulations strictly require. Your judgment degrades before you notice it. Finally, with anti-ice systems, the key word is proactive. Activate systems before entering icing conditions, not after. If the aircraft isn't certified for flight in icing, exit those conditions immediately. These takeaways, applied consistently, form the foundation of professional airmanship.